Okay, so let us continue our ring problems. So in this one, we have to find an integral domain in which we will have to find two distinct elements a and b such that their mth powers and nth powers are equal. They are not distinct for different positive integers m and n, that is distinct positive integers m and n. And the solution is very easy in the integral domain, because we should not just simply write ring. In the integral domain of the integers, we have these things. And we of course also have the fact that minus 1 and 1 are distinct. They are not equal in the ring of integers. They are equal only in the two element field having 0 and 1. And clearly our m and n values are also different. So this is an example. It's just this is the solution. Next, if A is an idempotent, A is an idempotent in a commutative ring, show that one minus A is also an idempotent. Idempotent means the square of A is A itself. A square equals A. So let me write the solution here. So we need to prove that 1 minus A is also an idempotent. That means we have to calculate its square. Using both the distributive laws, we can multiply the terms out like what we normally do with real numbers. So 1 times 1 is 1, minus 1 times A is minus A, minus A times 1 is again minus A, and minus A times minus A is plus A square. Now because A is idempotent, A square equals A, and that's how we have our 1 minus A back, and that is why 1 minus A is also an idempotent. We can just simply write hence is also an idempotent. Next, construct the multiplication table. A multiplication table for the ring Z2I, the ring of Gaussian integers modulo 2. We know what the elements in this ring are. They are elements which look like this: a plus bi, which look like complex numbers but they are not, because these components a and b are not real numbers. This time they are coming from this two element field z2 or z2, which we know that they are 0 and 1. That is, there are two elements which are 0 and 1. So each of these two things, a or b, they are going to be either 0 or 1. So accordingly, there will be only 4 elements in this ring, and we have to construct its multiplication table. Is this ring a field? That is another part of this exercise. And then also, is it an integral domain? So let us first construct the table. So in the table we are going to need 5 rows and 5 columns. We should of course start the solution by writing things like, say, the following is the table, but I am not going to write those things. You can do that. So the elements in this ring are these 4 elements: 0, 1, I and 1 plus I. 0, 1, I and 1 plus I. So multiplying anything with 0 is going to give us 0. So the first row consists entirely of 0, and so is the first column. Then multiplying anything with 1 gives that thing back, because 1 is the unity. So 1i, 1 plus I 1 plus I. The reason for having the same thing, the reason for having this matrix, a symmetric matrix, it is after all a matrix, no, whose rows are these and whose columns are these. The reason for having this as a symmetric matrix is that multiplication in this ring is commutative, that is why. Then I times I is I square. I square is going to give us minus 1, but we are having the elements a and b. I mean, in a plus bi we are having the elements a and b coming from z2. So that minus 1 would be in z2, and in z2 minus 1 is plus 1. So this is 1. Like that, I times 1 plus I is I minus 1, but this minus 1 again is plus 1, so we get 1 plus I. So this one is also 1 plus I, and then we need to calculate 1 plus I square. Now 1 plus I square is going to give us what? 1 plus 2I plus I square. 1 and I square will cancel out, and 2I is 0 because in Z2 2 is 0. So that is why this is 0. So this is the multiplication table for our ring. Now you can see that in this table we have a nilpotent element, a non-zero nilpotent element, and such a thing cannot be there in a field. In fact, it cannot be there in any integral domain. In other words, we can also say that 1 plus I is a zero divisor because it is non-zero, and we have found another non-zero element which is also 1 plus I, so that the product of these two is 0. So that is why it is neither a field nor an integral domain. If we can just simply say that it's not an integral domain, then automatically it's not a field, because every field is bound to be an integral domain. So we can just simply write after this that our ring is neither a field nor an integral domain. Since but 1 plus I whole square is 0, this is nor an integral domain. Next, the non-zero elements. So here in this next one we are going to consider a similar ring, but this time in place of this field Z2 or Z2 we are going to have Z3, but again with I mean Gaussian integers after all. The non-zero elements of this ring form an abelian group of order 8. There are 8 elements in this ring under multiplication. The multiplication that we have in this ring, under that operation, the non-zero elements in this ring form a group which is abelian. We need to figure out whether what 8 order group, abelian group, is it going to be isomorphic to? So is it isomorphic to this Z8 or this direct sum of Z4 and Z2 or the direct sum of 3 copies of Z2? It turns out, see, we know that this is a cyclic group of order 8, and this group that we have here, which the non-zero elements form, they also, it turns out to be a cyclic group, and hence it will be isomorphic to this because it's abelian also. So to show that these elements also form a cyclic group under multiplication, what we need to do, we need to show that under the multiplication operation there is an element in this ring which has order 8, and that element is 1 plus I. So we start the solution like this. To show that the group of non-zero elements of this ring under multiplication is isomorphic to this. It's enough to find an element, say A, in our ring this we need to show, and our candidate for A is 1 plus I. So we show that fact by calculating higher and higher powers of 1 plus I. Note that 1 plus I itself of course is not equal to 1. So we can start with the square of 1 plus I. 1 plus I whole square is going to give us what? 1 square plus 2I plus I square. Okay, and by the way, there is one more point. How am I able to write the normal expansion like what we do when we are dealing with real numbers? That's because just like the real numbers form a commutative ring, in fact a field actually, this one is also a commutative ring. Here also the multiplication is commutative. So the normal binomial expansion is true here. So 1 square plus 2I plus I square ultimately becomes 2I. So this is 2I, which obviously is not equal to 1. Then what about 1 plus I cube. This is 1 plus I whole square times 1 plus I, which is the same as 2I times 1 plus I. 2I times I is going to give us minus 2 because I square plus 2I. But minus 2 in this ring is what? 1. That is because 1 plus 2 in this ring is 0. So this is 1 plus 2I. This is also not equal to 1. Okay. Then 1 plus 2I whole to the power 4. For this we need not use this one. We can square this and get this fourth power. That means 2I whole square, which is 4I square, or minus 4. Now minus 4 in this ring is the same as 2 because 2 plus 4 is divisible by 3, which is also not equal to 1. Then 1 plus I whole to the power 5 is going to be what? 2 times, because this is the fourth power, 2 times 1 plus I. That means 2 plus 2I. This is also not equal to 1. Then the sixth power is the fifth power, that is 2 plus 2I times 1 plus I. For this we need to calculate. So this is going to give me what? 2 and 2I squared, that means minus 2. So 2 minus 2, they cancel out. And what about the terms where I will be there? 2 times I is 2I, and this 2I times 1 is again 2I, that means 4I. And in Z3, 4 is equal to 1, so here we get I. Then the seventh power, the seventh power is the sixth power, which is I times 1 plus I. So that means I square will be minus 1, that minus 1 is the same as 2 in Z3, and this extra I. And finally we will see that the eighth power will be 1. So what is the eighth power? The eighth power is the seventh power times 1 plus I. Okay. Now here, if we first look at the terms that will have I, 2I plus I means 3I, but in Z3, 3 is equal to 0, so I terms will vanish. And what about the terms where there won't be any I? 2 times 1 is 2 plus I square is minus 1. 2 minus 1 is 1. So see, here we are getting 1. So from this we see that the element 1 plus I in this multiplicative group has order 8. So that's why it is a generator of this group, and the group becomes cyclic group. So we can conclude things like this. Hence, we see that we can choose A equal to 1 plus I. So that multiplicative abelian group turns out to be nothing but this. and here the solution ends, and I end the video also here. We are going to solve more problems like this in the next Gallian ring theory update. And tomorrow we are of course again going to go through analysis. So with that I just wrap things up for tonight. So see you tomorrow with analysis. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.